So today I want to start with the lecture RF engineering, and in the first step I want to discuss with you what is the difference between, for example, RF engineering and electronics. You already did some lectures on electronics. For example, I sketched here an RC amplifier. It consists of different elements, and the question is now, from the theoretical point of view, what are the elements? So we use a certain schematic, and in this schematic we use different elements, for example, a voltage source, a resistor, and capacitor, and a BGT. And the question is now, what is common to all of these elements? And these elements are so-called lumped elements. In principle, from the physical point of view, this means all these elements are concentrated in a dot in space. So they only occupy a dot in space. So if you sketch a schematic like this, nobody knows in principle what is the size of all these elements, and this RC amplifier from the physical point of view is just a dot in space. This, as a result, our theory, if we describe this circuit with our network theory of lumped elements, we don't account for the physical size of the elements. And this is different in RF engineering. And RF engineering is the first lecture where we will account for the physical size of the elements, and this is done especially by describing wave propagation. And of course, if we discuss waves, or if we discuss elements in RF engineering, we have especially the transmission lines. The transmission lines have a very big size, so they are, normally we say they are directed in the Z direction somehow, and we must account what happens if we discuss a transmission line, what happens on this transmission line. So in the first step, what we will do now is to go and discuss the so-called transmission line theory. So to account for the physical size, we will now start with the so-called transmission line theory. I sketched here an XY Z-plane, so if you have a right-handed coordinate system, then you have X in this direction, Y in this direction, and Z in this direction. And what I sketched here is a cross-section of different transmission lines. For example, in the first picture I sketched the fields, the electric field and the magnetic field of a coaxial transmission line. And normally the outer conductor of a coaxial transmission line will be connected to the ground potential. In the next picture I sketched also the field or the cross-section of a so-called two-wire line with the electric field and the magnetic field. And what is very famous in RF engineering is the so-called microstrip line. It consists of a ground plane, which is also connected in principle always to the ground potential and the strip. And the strip is attached to the top of a so-called substrate. And this substrate has a certain epsilon r. We have here, I sketched also the electric field and the magnetic field. And of course, all these lines do not change in the Z direction. It means, again, they are homogeneous in the Z direction. And now we must at least assume that the voltage and the current will be a function also of the Z direction. So what we do now, I always in principle sketch a two-wire line, but this theory we set up is also valid, for example, for the coaxial transmission line, also for the microstrip line. So to sketch this line, I always sketch in principle two wires. And what we must do now is we introduce here a coordinate system. And I introduce here always a z coordinate system. This means now in the z direction, these lines do not change. They are homogeneous in the z direction. And to account for the size now, we introduce here the voltage between the two lines, which must be a function of the space coordinate and the time. And also the current we will introduce here will be a function of the space coordinates and the time. So the question is now, what are these functions looking like, or how do they look like as a function of the space coordinates and the time? In the next step, we will assume not an arbitrary time dependence, but always a sinusoidal time dependence, and this will simplify our theory, and this we will discuss in the next step. To simplify our problem, we will use now phasor notation to describe sinusoidal time functions. So we don't use arbitrary time function, but sinusoidal time function. In principle, we have that we assume, for example, for the voltage, that the voltage is a function of the space and time coordinates. But now we will not use an arbitrary time function, but a sinusoidal time function. This results in the fact that the amplitude itself becomes a function of the space coordinates, sinus omega t plus, and also the phase may change of this time function, so we have to introduce here phi of z. So also the phase shift may be a function of the z coordinate. To go on or to deduce now the phasor notation, we remember Euler's law. And according to Euler's law, we have that the exponential function exponent jx can be written as cosine of x plus j sinus of x. So you see, with the help of the exponential function, we can also express the sinus function if we only consider its imaginary part. So we have that sinus of x is just the imaginary part of our exponential function jx. If we would consider the real part, then we would express the cosine function, but both functions are sinusoidal. So what we can say now, that the voltage as a function of space and time can be written as u of z. So this is an amplitude. Of course, an amplitude is always positive, this we will use later, times the imaginary part of now the exponential function, and we have to write here exponential function of j omega, or here we have to open omega t plus phi of z. So these two terms are identical, and since this voltage itself is a positive function, we can put this into the bracket term, and we will have, and in the next step we can also separate the exponential function in the product of two terms. So we will have the imaginary part of u of z, this is the amplitude, times the exponential function of j phi of z times the exponential function of j omega t. And what we will do now, we will introduce a phasor to describe this term. This we say this is our phasor u of z. It's a complex valued function and it's defined by the amplitude as a function of the z coordinate times the exponential function of j phi of z. This is now our so-called phasor. These phasors are in principle also used in AC electronics or AC circuit theory, but in AC lumped circuit theory they are not a function of the z coordinate. And if we go back to this point, we can say as a result, if we know the phasor, we can find that u of z will be equal to the imaginary part of our phasor times the exponential function j omega t. So this is the equation how we can switch back from the phasor notation to our sinusoidal time function. Perhaps I summarize this again. So using Euler's law, we can substitute the sinus function by the imaginary part of the exponential function, and inserting this and remembering that the amplitude is a positive function, so we can put this into the bracket term and we define this to be our phasor. And this is the phasor you already know from AC circuit theory, but here we will the phasor of the voltage will be a function of the z coordinate. And we can use this equation to switch back from our complex valued function. In the complex valued function you don't see any time dependence anymore, so you must remember what frequency you are considering, and then you can switch back to our sinusoidal function, which is a function of not only the time but also of the z coordinate. So I want to deduce now the so-called equivalent circuit of a lossless transmission line section. What I did here, I sketched again our transmission line, and we started to describe our transmission line with arbitrary time functions, which are also function of the space coordinates. Then we use phasor notation, and we assume that now the function are not arbitrary function of the time, but sinusoidal function. This results that we use now phasors to describe, for example, the voltage at a certain point in space. So we have the voltage at a certain point at a certain z coordinate, and here we will also have a current flowing at this z coordinate, which is also of course a phasor. What I now want to assume that we have here a certain coordinate z, and we discuss now the influence of a section of this transmission line. I assume here now that we have here the coordinate z plus delta z. And what I want to do now, I want to in principle magnify now this section of the transmission line and describe this section by an equivalent circuit. So here we have the z coordinate. And here I assume to have the coordinate z plus, over here, z plus delta z. This means we define some planes in the transmission line at z coordinate and at the point z plus delta z. As a result, we will have here the voltage U of z. Of course, in this knot we will have the current flowing E of z plus delta z. E of z. Here we have I of z. And at this point we have flowing the current E of z plus delta z. Here we just use, this is not a line, but in a mathematical sense these 2 points are identical. So, and here we have the point, the voltage U of z plus delta z. And the question is now, how do we have to construct this equivalent circuit? Therefore, I want to sketch here again a 2-wire line. And we remember when we draw the 2-wire line, of course, the current which we will have here, the current is flowing in this direction. Here we have the z direction. Though this current will result in magnetic fields surrounding this line. And if the current is flowing in this direction, then the magnetic field lines will be like this, and this is the magnetic field. And of course, everywhere where we have stored magnetic, or where we have a magnetic field, then there will be, in this section, there will be stored magnetic field energy. And to describe the stored magnetic field energy by a lumped element, we will introduce here an inductance, but we will say this inductance is L prime times delta Z, and we can say the magnetic field between the lines will result in a L prime, which is an inductance per unit length and it will be measured in, for example, nanohenry per meter. So you can say, independent of which kind of transmission line you want to describe, every transmission line will be described by a so-called inductance per unit length, and this, the inductance per unit length, will describe the stored magnetic field energy in this transmission line section. Beside the magnetic field, we will also have an electric field. So the electric field will be, look almost like this in a two-wire line. So we have here the electric field. And of course, if there is electric field between the lines, in this section we also will have stored electric field energy. And the stored electric field energy will be represented by a capacitor C primes times delta Z. So the influence of the stored electric field energy between the lines will be represented by this capacitance, and we have here the C prime. This will be the capacitance per unit length and of course this will be measured in picofarad per meter. This results in the fact that every transmission line which we consider, we must know its capacitance per unit length, and then we can, with the help of the capacitance per unit length, we describe the influence of the stored magnetic field energy, stored electric field energy. So the two elements we introduced here only represent elements which store field energy. They don't dissipate field energy, but as you remember, if a current is flowing along the line, of course the line itself will heat up by the current, so we must include additional elements which will describe the losses in this transmission line. So this we will do in the next step. So up to now we discussed the equivalent circuit of a transmission line section without losses, or a lossless transmission line section, and the essential elements we had to use were the inductance per unit length, which described the stored magnetic field energy between the wires of the line, and we have to account for the stored electric field energy, and this is done by including a capacitance per unit length. But as I already told you, if a current, of course here, is flowing in the line by offset, of course this current will result in a heating of a line, because the line will have a certain resistance. And so what we have to do is to introduce here an additional element, R prime times delta Z, and R prime is then the resistance per unit length, and this resistance per unit length will account for the losses. As soon as a current is flowing along the line, this current will heat up the line, and these losses are described by our resistance per unit length. Of course, the unit would be ohm or milliohm per meter. The next element we have to account for is, of course, the capacitor. You know, a real capacitor will always show some losses, and to account for the losses we must introduce here a further element which we will call G primes times delta Z, and G prime will be the conductance per unit length, and it will be measured by 1 over ohm, perhaps I'll write it like this, ohm per meter. So this will be the conductance per unit length. Of course, for example, if you would have a open transmission line and you charge up this open transmission line, after a certain time it will be decharged. So this must be accounted for by the inductance per unit length. Now we have in principle here the equivalent circuit for a small part of a small section of the transmission line, and now we can try to set up the equations which relate the currents and the voltages. Up to now we deduced this equivalent circuit for a small section of the transmission line, and of course at the moment we don't know the function u of z and I of z, and if there are some functions which are unknown, you have to set up some differential equations describing these functions. And this we will do in our first step. And what we have to do is now to apply Kirchhoff's law, and in the first step we will apply Kirchhoff's voltage law, KVL, which results in the definition of a mesh equation. I define here a mesh, we call this mesh M, and apply here Kirchhoff's voltage law. This means in the sum of a mesh all voltages must sum up to zero, where you have to account for the direction, of course, of the currents and the voltages. So you see here, if we sum up this voltage, we will end up in minus u of z, because we sum up against the direction. And here you see the current I of z will flow through this series element, so it will result in a plus R prime plus J omega L prime, because we use phasor notation here, and we must multiply with delta z. This will be the impedance of these series elements, and of course you see here the current I of z is flowing through these elements, so we have to multiply here with I of z, and we have to add here the voltage plus u of z plus delta z. And of course this must be zero according to Kirchhoff's voltage law. Now we can separate the voltages and the current, so we bring this to the other side and we can write it like this: minus u of z plus delta z minus u of z. This will be equal to R prime plus J omega L prime times delta z times I of z. So this is the result now, or is one step in between. We are not at the result, but what we will do now is we will divide the whole equation by delta z, and so we will end up here in minus u of z plus delta z minus u of z divided by delta z, and this will be equal to R prime plus J omega L prime times I of z. And as I already told you, we must end up in differential equation. This results in the fact that we have to consider here the limit delta z tending to 0. It means we consider a very, very small or thin plane in the transmission line, and if we have a look to this expression, this is nothing else but the definition of the differential equation, differential of the voltage as a function of the z coordinate. So we have here, this is u of z divided by dz, or we have to derive the function u of z with respect to z, and this is now equal to R prime plus J omega L prime times I of z, which shows us that we have found here the first differential equation which relates the voltage function and the current function. Again, I want to point out we don't know the current function I of z, but also we don't know the voltage equation. But since we have two unknown functions, we need a further differential equation. To deduce a further differential equation, we now use KCL, Kirchhoff's current law. Again, in this case, we consider a certain knot, the knot equation of this knot. For this knot, we will formulate now Kirchhoff's current law. And you see the current I of z is flowing into the knot. So we will have I of z will be equal. Here the current I of z plus delta z will flow out of the knot. So we will be equal to I of z plus delta z. And of course, a certain current is flowing through the parallel elements, which will be plus G. Now we have to add the conductances because they are in parallel, plus J omega C prime times delta Z times U of Z. And again, we can bring this to the other side, so we will have here I of Z minus I of Z plus delta Z minus I of Z. This is equal to G prime plus J omega C prime times delta Z times U of Z. And again, we will divide. Oh, sorry, here I did a small mistake. Here it must be written U of Z plus delta Z. And here also it must be written U of Z plus delta Z. But what we do here, we divide by delta Z. So we can write this as minus I of Z plus delta Z minus I of Z divided by delta Z. This will be G prime plus J omega C prime times U of Z plus delta Z. And again, what we will do now is that we will have a look to the limit delta Z tending to 0. Then again, you have here the differentiation of the function I of Z with respect to Z. So this is minus di of Z derived with respect to Z. And of course, if you consider the limit delta Z tending to 0, then this will become 0, and we will have this is G plus J omega C prime times U of Z. What we have now, we have here now the second differential equation, which relates the two functions I of Z and U of Z. What we found out now by analyzing this small equivalent circuit, we used at one hand KVL, Kirchhoff's voltage law, for this mesh, and we used KCL, Kirchhoff's current law, for this knot equation, and then we consider the limit delta Z tending to 0. That means we have a look to a very, very small section of our transmission line, and with the help of this consideration we found these two differential equations, and these two differential equations relate now the current at a certain point set to the derivation of the voltage, and this is the decay of the voltage, because if the voltage decays, this will be positive. And also here we have the decay of the current is related to the voltage at a certain point in space. And in the next step we will combine these two functions, differential equations.